The second objective is to illustrate when work is positive, negative, or zero with suitable examples. We've summarized the three cases of the sign of work using this table. When the angle between F and D is less than 90, it's an acute angle, the work would be positive, the speed of the object would be increasing, and the object gain energy. This includes the angle 0, where F and D are in the same direction. If F and D have an angle 90 degrees between them, then the work is 0, the force does no work. The speed of the objects is left unchanged, doesn't change, doesn't increase or decrease, and as well as the energy of the object, it stays the same. But if the angle between the applied force and the displacement or the direction of motion of the object is between 90 and 180 degrees, this includes when F is opposite to D, the work would be negative, the speed of the object decreases, and the object loses energy. We've further verified these using this analogy. You can see if the external world, such as these people, are doing work on the system, which is the bus in this case, the work done on the bus would be positive and the energy of the system increases. That because this bus will move towards the left and the force applied is also towards the left, so the work would be positive. And the energy of the bus increases because the bus will gain speed, it will accelerate. But if the system does work on this external world, so for example, if you are doing work on your environment, then the work would be negative. You can apply the equation on different situations and find out that the work would be negative and the energy of the system decreases. Just like when you throw an apple upwards. Well, if you throw an apple upwards, it's traveling upwards, but the force of gravity would be down. Now, the object would start to slow down as you throw it up because the force of gravity is doing negative work on it. Means that it slows the apple down and it's losing the energy. The apple starts losing the energy. You can see that the angle here is 180 degrees. We have this question mentioned in the objective. You have a bicycle and a bicycle rider pushes this bicycle that has a mass of 13 kilograms. So this is the mass of the bicycle. He pushes this bicycle up a steep hill. The incline is 25 degrees. The incline is 25 degrees. So this is phi. This is the angle of inclination, just like we have learned in term 2. The hill is 275 meters long. So the distance traveled by this bike is 275 meters. Okay, so the distance traveled by this bike, we can draw it here, is 275. So this is the distance or the displacement traveled by the bike. It's the same as the length of the hill. The rider pushes the bike parallel to the road. So the force that the rider is applying is also parallel to the road. Let's draw it here. The force of the rider is 25 newtons and it's parallel to the road. You can see that the angle between them is 0. The angle between the force applied and the displacement is 0. They are on one another. There is no angle between them. So this is the force applied by the rider. The rider pushes the bike parallel to the road with a force of 25 newtons. So this is the force applied by the rider. Question A says, how much work does the rider do on the bike? So he wants me to find the work done by the rider. You can call it work rider equals to the force applied by the rider multiplied by the distance traveled by the bike by cosine the angle between them. The force of the rider is 25 newtons. The distance traveled by the bike is the same as the length of the hill, which is 275 meters. And the angle between the force applied and the displacement is 0. There is no angle between them. That will give you 25 times 275 times cosine 0. Remember, cosine 0 is 1. So that's going to give you, oh, sorry, I made a mistake. It's 25, not 22. 25 times 275 times cosine 0 equals 6,875. 6,875 joules. Question B says, how much work is done by the force of gravity on the bike? Now you can solve this in two ways. You can either find the angle that the force of gravity, remember the force of gravity is always downwards, like this. This is the force of gravity. You can find the angle between them and then use the equation. Or you can remember that the force of gravity on an incline can be broken down into its x and y components. That means that the force of gravity can be broken down into its y. This is the y component of the gravitational force, and the x components. This is the x component of the gravitational force, Fgx. Right, now you can see that the angle that the force, the y component of the gravitational force makes with the displacement, this is the angle, see? Now that after you find Fgx and Fgy, there is no need for Fg anymore. But you can see that Fgy, the y component of the gravitational force, makes a 90-degree angle with the displacement. That means that this one does not work, since it's perpendicular to D. So the only component of the gravitational force that does work is the x component. So for question B, you need to find the x component of the gravitational force. So let's find the x component of the gravitational force. Fgx can be found by multiplying mg sine phi. That's something that we have taken in term 2. The mass of the bike is 13 kilograms and g is a constant number. It's a 9.8. Cosine phi, which is the inclination angle, زاوية الميلان. Here it's mentioned to be 25. So Fgx is 13 times 9.8 times 9.8 times sine mg sine phi times sine the 25 close bracket. That gives you 53.8. So m times g times sine 25, that's 53.8. Now that we found the force, we can find the work done by the gravitational force by multiplying the x component of the gravitational force, remember it's the only component that does work, times the displacement traveled by the bike times cosine the angle between them. So 53.8 times the distance traveled is 275 times cosine the angle between Fgx and D. Now from the image you can see that Fgx is down the incline and the displacement is up the incline. The angle between them, let me make it as clear as possible. The angle between Fgx and D is 180 degrees. Using the calculator, we're going to multiply this number times 275 times cosine 180. Remember, cosine 180 gives you a negative. So it's negative 14,806.4. All right, let's solve this question. In this question, it says the box in the diagram below was pushed over the ramp with a net force of 100 Newton. So given is the force applied on the box, 100 Newton. Question says what is the work done on the box to move it from the bottom of the ramp to the top? Now we can see that if I wanted to find the work done on this box by multiplying the force given, I find out that there's the distance missing. So how can I find the distance traveled by the box? Now the box was here and it traveled all the way here. The distance traveled by the box is the same as the hypotenuse in this triangle. How can I find the hypotenuse of a triangle? This side of the triangle is called the hypotenuse. It's the longest side in a right angle triangle. How can I find this hypotenuse? I use the sine trigonometrical function. Here we have an angle, we have an opposite, and we can find the hypotenuse using the sine. Sine, the angle given in the question, is equal to the opposite to that angle divided by the hypotenuse. Now the angle is 30 equals the opposite of that angle, the side of the triangle that is opposite to the angle is 3, divided by the hypotenuse, which is the same as the distance traveled by the box. Now I use the shift equation to find d, or I rearrange the equation. To rearrange the equation, d would become 3 over sine 30. Or you can use the shift solve on the calculator to find d. So 3 divided by sine 30 is given to be 0.5. 3 over half, or 3 over 0.5, it gives you 9. So 3 over half is 3 times 2, which is 6. Alright, so we have the distance, we have the force, now we can find the work. The force is 100 newtons, the distance is 6 meters. Cosine the angle between them. You can see that this box is traveling up the incline, and the force applied is also up the incline. So the angle between them is 0. 6 times 100, that's 600 joules. Cosine is 0, it gives you 1. So the answer is 600 joules. This question here says, in which of the following cases the work done equals to 0? Remember that when the angle between F and D equals to 90, the work done by that force is 0. Here, both of them in the same direction. Here also, both of them in the same direction. Here they have an angle, but it's not 90. So here, in this case, the force up than the distance or displacement to the right. So the angle between them is 90, and the work done would be 0. Similarly, here we have the force applied on the ball is towards the hand of the person, and the displacement is always perpendicular to it in circular motion. So the angle between F and D is 90, and hence the work done by that force is 0. In this question, which of the following figures represent a total positive work done by the external force on an object? To have a positive work, the angle must be 0, bigger than 0 and less than 90, or 0. Here you can see that the force applied is towards the right and the box is moving towards the right. So here we have positive work. Here we don't have any work because the angle between them is 90. You can see the force is down and the direction of motion, which is the same as the direction of displacement, is towards the right. So the angle between them 90. Here we have the force down, but the displacement up. That's 180, and it gives you a negative work. And similarly here, we have a net force of 0, so there's no work. Right, so in the first case only, where F and D in the same direction, we have a positive work. You can see here also, here the force applied by the man is up, and the displacement or the direction of motion is towards the right. So this person is doing no work. Here also, the man is lifting the box upwards, and the displacement is upwards, or the direction of motion is upwards, and hence, because F and D in the same direction, this man is doing work. And this question says a box is pulled to move on the floor for a distance d as seen in the figure. What is the work done on the box by the normal force? Now you can see that the normal force and the direction of motion or the displacement have a 90-degree angle, so the work between them is 0. According to the work energy theorem, which of the following is not correct? If external world does work on the system, remember that the work would be positive and the object gains energy. The work would be positive and the energy of the system increases. So this is correct. I'm looking for the incorrect one. Work done on the system is equal to the change in the system's energy. This is the work energy theorem. This is also correct, which states that the work done on an object is equal to the gain or loss in its energy. It's equal to the change in its energy. If the external work does work, if the external world does work on the system, the work is negative and the energy of the system decreases. This is the opposite of the first sentence, so this one is the incorrect one. If the system does work on the external world, remember the tired Smurf, then the work is negative and the energy of the system decreases. The third one. The third one is incorrect.